There's a coating system that can do something most people in the coatings industry would have said was impossible 10 years ago. Something to replace 2 or 3 coats to one coat system. Go from days of downtime to a few hours, and still hold up under UV, weather, and heavy wear. That system is called Polyaspartic. Welcome to AetherLab PolyCoatings. This is the series where we break down the science, engineering, and real-world performance of industrial polymer coating systems. In the past episodes of PolyCoatings, we saw that epoxy is the workhorse, exceptional adhesion, outstanding chemical resistance, excellent barrier properties. It is used as primers, floor systems, tank linings, but it yellows outdoors. Polyurethane brings what epoxy lacks: UV stability and gloss retention, the go-to top coat for exterior applications. Polyurethane top coats solve the UV problem, but it brings other issues. It generally needs a tin catalyst, which can drive a side reaction with moisture-generating carbon dioxide gas. That means bubbles in thick films, so that limits you to 3 to 4 mils per coat. Further, it is sensitive to humidity and almost always need an epoxy primer underneath. So, you are back to multi-coat systems with multi-day schedules. Polyaspartic coatings were designed to tackle some of these challenges: lower number of coats, faster return to service, UV stability, ambient cure, and near zero VOC at point of application. But here's where most people get it wrong. Polyaspartics are often grouped with polyurethanes. They are not polyurethanes. The chemistry is different. The reaction is different. Developed in the early 1990s, polyaspartic chemistry is relatively new, and number of companies that truly understand it is still small. But the coatings built on this chemistry are replacing systems that have been used for decades. Let us start with the most important question. What exactly is a polyaspartic coating? Before we talk about products, formulations, or applications, you need to understand where polyaspartics sit in the coatings chemistry family, because this is where most confusion starts. First, let us look at how polyaspartic coatings differ from a polyurethane or polyurea coatings. Polyurethane. A polyurethane is formed when a polyol, a molecule with OH hydroxyl groups, reacts with isocyanate. That gives you a urethane bond. We quickly glanced at its fundamental advantages and disadvantages earlier. Polyurea. Here, instead of a polyol, you use an amine plus isocyanate gives you a urea bond. There is no need for a catalyst and there is no carbon dioxide generation from moisture, but the reaction is extremely fast. Gel time is in seconds. This means lower pot life, no brush or roller application, and required plural component spray equipment. And here comes polyaspartics. It is a type of polyurea and not polyurethane. The difference is on the amine side. Instead of a conventional, you use an aspartic ester. Chemically, this is a sterically hindered secondary diamine. And that steric hindrance, those bulky ester groups around the nitrogen, it slows down the reaction. Not seconds, 10 to 60 minutes of working time. That single change gives longer pot life with brush, roll, or spray application, fast cure with no catalyst, and you are still forming urea linkages. Same bond, same base chemistry, just controllable. In a conventional 2-component polyurethane, you are limited to roughly 3 to 4 mils per coat before you risk bubbling from carbon dioxide. With polyaspartics, you can go 6, 8, 12, and even 16 mils in one coat without bubbling. That is not a small improvement. That is a system-level shift in how coatings are applied. Everything about a polyaspartic system starts with one thing: base resins, or the aspartic esters. Let's have a quick look at what it is. Aspartic esters are formed by the Michael addition reaction between a primary diamine and a dicarboxylic acid ester. Examples of the reactants are as follows. Let us look at an example. Methylene bicyclohexylamine, or PACM, were to react with DEM. The active hydrogen atom on the primary amine adds across the double bond of the acid ester, converting into a second-day amine. This reduces the reaction rate with isocyanate. Further, the primary diamines selected in aspartic ester synthesis have bulky ester groups. This steric hindrance further reduces the reaction speed. These aspects are the reasons why polyaspartics is different than a polyurea and why they work so well. The real control variable is the backbone primary diamine, the X group between the two aspartic units. Change that backbone and you can change reactivity, pot life, viscosity, and application method. That is how entire product lines are built. A handful of companies make aspartic ester resins. We will cover them in the market section, but Covestro, then known as Bayer, invented this chemistry in the 1990s, and their Desmofin NH series is the benchmark everyone else positions against. So that is where we start. Formulators often use blends to achieve optimized performance. Now, LF variants are a critical real-world detail. Standard aspartic esters contains a reaction byproduct called the fade or the DEF, sharp, noticeable ester odor. That's why the LF grades or the low fade grades, it has less than 0.1% fade content, low odor, and better color stability. Let us look at the cure or hardener side of the polyaspartic coatings. While the aspartic ester controls how fast the reaction happens, the cure side selection plays a major role in the final cross-link density, flexibility, chemical resistance, durability, and film hardness. Aromatic isocyanates like the MDI and TDI contains aromatic rings in its backbone and absorb UV radiation, resulting in yellowing over time. And polyaspartics are mostly used as top coat, where we need excellent UV stability. So almost always, the cure side is an aliphatic isocyanate like the hexamethylene diisocyanate or HDI. The most dominant component used here is isocyanurate trimers or HDI trimers, where its molecules are linked through a 6-membered ring. That ring is thermally stable, UV stable, and gives the crosslinker its weather resistance. Shown here are commercial HDI-based hardeners from Covestro, with each grade engineered to impart distinct properties within a formulation. Let us look at the cure math, the NCO and NH index or stoichiometry. If you get this wrong, you end up with a coating with inferior performance. The core principle is that every reactive NH group in the aspartic ester must be matched with an NCO group. This determines your NCO, NH mix ratio, and we would need amine hydrogen equivalent weight or AHEW and NCO equivalent weights. If you are using a blend of resins in the formulation, usually the ratio is kept 1 to 1.05. Slight excess of isocyanate ensures complete amine consumption. And if you are wondering what happens if you miss, too much NCO results in a hard, brittle film with possible surface defects. And too little NCO results in a soft, tacky coating with poor chemical resistance. Let us now look at how polyaspartic cure is different. First, there is no catalyst driving the NCO water side reaction, no bubbles, and thus thickness up to 18 mil possible. More temperature tolerant than conventional 2K polyurethanes. Faster cure with practical working time. Even if humidity is a factor, since NCO groups on cure side can react with atmospheric moisture, its impact is dramatically less than catalyzed polyurethane systems. This can be controlled by selecting the right hardener and moisture scavengers. Moreover, the amine blush, or the waxy haze that you see in epoxy amine systems, are rarely seen with polyaspartic coating. The steric hindrance discussed earlier that slows down the cure also prevents the surface reaction leading to amine blush. Let us now have a quick glance at the formulation basics to build a real system. Obviously, a practical polyaspartic formulation is more than just the resin and the hardener. It also includes other components. Reactive diluents, like NH1720, help reduce viscosity while maintaining 100% solids. And even when most polyaspartic floor coatings are 100% solids, solvents like butyl acetate, xylene are used for spray applications in automotive refinish and industrial top coats. Pigments and fillers used in polyaspartic coatings should not contain any moisture, as it can react with NCO groups and create bubbles and defects. For the surface additives, non-silicone-based additives are preferred for flow, leveling, air release, and clarity. This is because sometimes silicone additives in the polyaspartic system can cause recoat difficulties and slight haze with temperature or humidity spikes. Instead, non-silicone additives like polyacrylates can provide better recoat, clarity, and degassing. As moisture scavengers for polyaspartic systems, reactive oxazolidanes are preferred over zeolite powder molecular sieves, as the latter absorb moisture. Now we look at the polyaspartics coatings markets and industrial applications. Flooring is the largest market. A 2-car garage can be done in one day with primer, decorative chips, top coat or sealer, and now it is walkable by evening, same day. With epoxy, that same job can take days until you can walk on. And here, for the contractors, speed equals money. Next comes corrosion protection. Polyaspartics can eliminate the intermediate epoxy coat, zinc primer, and a polyaspartic top coat. That's it. Take a bridge, for example. Fewer coats, less time, same protection. Next is industrial OEM and automotive refinish. From single coat direct to metal coatings for agricultural and construction equipment, to putty and clear coat for automotive refinish, these polyaspartic products cure at room temperature, and energy savings are up to 80%. Another market is the wind energy market. Polyaspartic-based gel coats and flexible systems with leading-edge protection performs well here. Finally, the waterproofing membranes and sealants. Example would be crack bridging membranes for balconies and terraces, UV stable pourable joint sealants. Next, we look at who makes and sells these polyaspartics. The manufacturer and supplier market can be categorized into 3 layers: raw material suppliers, global coatings companies, and specialist floor coatings brands. Next, we have the global coatings companies with polyaspartic product lines. Finally, we have the US specialist floor coatings brands and couple of franchise and dealer networks. This is where the actual contractors market lives, highly fragmented. Now let us look at some of the limitations of polyaspartics. Every chemistry has practical trade-offs. Polyaspartics are no exception. First comes cost. Polyaspartics contain specialty chemicals and cost more than epoxy. It is important that you factor in labor savings, fewer coats, and faster return to service in the total project cost. Pot life can still be an issue, and polyaspartics would require disciplined crews and small batches. Fast cure is productive, but it also makes it unforgiving. On the job site, a slower backroll, wrong mix ratio, and substrate moisture, all of these factors can cause problems. Next, even the direct-to-metal polyaspartic coatings need well-prepared metal for the best adhesion, and especially for the highest corrosion protection, as zinc-rich or epoxy primers are almost always recommended underneath. Next comes the chemical resistance. Polyaspartics provide good chemical resistance. However, an epoxy novalac or similar systems outperform polyaspartics in concentrated acids, alkalis, or aggressive solvents, so polyaspartics are optimized for UV stability and productivity, not the harshest chemical service environment. Next is the odor. Despite zero VOC claims, polyaspartics are not odor-free and can contain fade and residual NCO odor. Low odor grades and good ventilation can solve it, but it does add the cost and complexity. Finally, the supply chain. There is no diversified supply chain like polyurethanes or epoxy. This small supplier base can make it very sensitive to supply disruptions and limited options. Yes, these are real limitations, but in right application, the advantages still dominate. As of 2026, the polyaspartics market is approximately $400 million, growing at 5 to 6% annually. The chemistry is only 30 years old. Supplier base is still small and the formulation expertise is concentrated. This makes it a competitive advantage for anyone who takes the time to learn it. We are building the most comprehensive and practical polymer resource on YouTube. One chemistry, one application at a time. Next episode, we will dive deep into the epoxy systems. Like, share, and subscribe to Polynovel and turn on notifications so you do not miss the deep dives coming in this series. Thank you for watching.